Precisely, precisely at this point, at least from the perspective of a philosophical cautionist sort like Jim Peebles, cosmology departed from science, passing from math to myth. You couldn't know how the universe began because the evidence was out of reach, just as it had been for Aristotle, Ptolemy, and Copernicus. They couldn't go across space to retrieve it. You couldn't go into the past. All you could do was observe the present phenomena, these redshift galaxies, and try to find the math to accommodate their motions. All you could do was try to save the appearance. If that was your idea of science, Hubble himself, as an observer, hoarding evidence and leaving the theorizing to the theorist, preferred to remain agnostic as to whether the universe really was expanding or whether another interpretation might explain the appearance correlations. But some theorists couldn't resist the challenge of rewinding the film. The Belgian priest Georges Lemaitre, a physics and astronomers, imagined the expansion unreeling in reverse, the size of the universe shrinking, smaller and smaller, the galaxies rushing back together, faster and faster, until the infalling matters would reach a state that he called the primeval atom, and that other astronomers will come to call a singularity, an abyss of infinite density and incalculable mass and energy. But words such as infinite and incalculable aren't for much use to mathematicians, physics, or other scientists. The unrestricted repeatability of all experiments is the fundamental axiom of physical science. Hermann Bondi and Thomas Gold, Austrian expatriates living in Britain, wrote in the first line of paper they submitted in July 1948 that outlines an alternative to Lemaitre's theory. The following month, their friend Fred Hoyle, a British astronomer, submitted his own variation on the theme. Rather than the Big Bang, the term Hoyle applied during a BBC radio broadcast in March 1949 to the idea of a universe expanding form, as he wrote in his paper, causes unknown to science. They postulated a steady state through continuous creation of a matter. Hoyle wrote, it might be possible to obtain an expanding universe in which the proper density of matter remains constant. Over the course of cosmic history, the creation of even infinitesimal amount of matter would become accumulative significant. Such a universe wouldn't have a beginning or an end, it would just be. For many astronomers, however, continuous creation was no more appeal than a singularity. Both the Big Bang and steady state theory seems to require a leap of faith, and faith not being part of the scientific method, there they let the matter rest. But what if there was evidence from one theory or the other? Bob Dick asked Jim Peebles this question one sweltering evening in 1964. Peebles had arrived at Princeton as a graduate student 6 years earlier. At the University of Manitoba, he had been the top student in physics, winning Academy honor after honor. At Princeton, he was shocked at how much physics he didn't know. He spent his first year trying to catch up, and then one day some friends invited him to get together that Dick ran most Friday evenings in the attic for Palmer Physics Laboratory. The Gravity Group was an informational gathering of dozens of undergraduates, postdoc, and senior faculties. Dick Bird, they called themselves. People went, and then they were back. He began to understand that they're in a sometimes stifling setting in an inconvenient hour. He could get an education, eating pizza, drinking beer, and try to figure out how to rehabilitate general relativity relativity had been around for nearly half a century. Einstein had arrived at the equation in late 1915, whereas Newton imagined gravity as a force that acts across space. Einstein's equation cast gravity as a property that belongs to space. In Newton's physics, space were passive, a vessel of mystery force between masses. In Einstein's physics, space was active, collaborating with matter to produce what we perceive as gravity effect. The Princeton physicist John Archibald Wheeler offered possibly the pithiest description of this codependence. Matter tells space how to curve. Space tells matter how to move. Einstein, in effect, reinvented physics. Yet by 1940, Dick could ask a professor of his at the University of Rochester why the graduate physics curriculum didn't include general relativity, and that the answer was that two had nothing to do with each other.